Hello everyone. We are given the following circuit and asked to find an RL that will absorb the maximum average power, then find the maximum average power absorbed. Our strategy for this circuit is we are going to remove the load resistance from the current left hand of the circuit and find the Thevenin equivalent. So we will actually have our points A and B right here, and we are going to find the Thevenin equivalent first. And because we are given a voltage source when finding the Thevenin resistance, we are actually going to short it. When we do that, we create the following circuit with the voltage source shorted and the load resistance removed. When calculating the Thevenin resistance, we are going to start right from A. Going in, we can see that we have a series of minus J50 Thevenin equal to minus J50, and then when we come here, we can see that the 50 resistor is in parallel with the 50 plus J50 resistor. So we're going to use the parallel formula for resistance, which is R1 times R2 over R1 plus R2, and get the following. 50 times 50 minus plus J50 over 50 plus 50 plus J50, and this is actually going to give us 30 minus J40 ohms. And moving on, one thing to note here is in the original, our load resistance is purely resistive. Therefore, the imaginary part of our load resistance is automatically 0 ohms. So what we're actually going to do is our load resistance is going to be equal to the magnitude of our Z Thevenin, which in this case is going to be the square root of 30 squared plus 40 squared, which is going to give us 50 ohms. And this is going to be our load resistance to find the maximum power. Now that we found our Z Thevenin and our load resistance, we're actually going to find V Thevenin. To find V Thevenin, we are actually going to find the voltage drop from terminal A to terminal B. And as we can see with terminal A, because it's not in a closed loop, the voltage drop from terminal A, the voltage at terminal A is going to be equal to the voltage at this point where we between the 50 resistors. And because of that, we can actually use what's known as a voltage divider. So V Thevenin will be equal to the total resistance from A to B, which is 50 plus J50 ohms, over the total resistance of our circuit right here of 50 plus 50 plus J50 ohms times our voltage source, in this case 150. And that will give us the following of 90 plus 30J volts. And for this equation, we are actually going to leave that in its complex form because we do not need to find its phasor. Having found both Z Thevenin and V Thevenin, we're going to redraw the original circuit from up here into the following, where we have V Thevenin and Z Thevenin, and we will reattach our load to it and to calculate the P max. And since we're finding the average power, we're going to say that P max is going to be equal to 1/2 over V max I max. And in case you're not familiar with it, there's also a second part of the equation that we're leaving out, which is cosine of theta V of our theta current through that resistor as well. But because we are finding the average power, this is actually equal to 1 due to theta V equal to theta I. And so all we have to do is find P max is equal to 1/2 V max I max. And we're going to actually write this equation so that we are finding the following: 1/2. We're going to replace Vmax with our load resistance, Imax, to get the following equation: RL times Imax squared. And then Imax is actually going to be equal to the magnitude of our current. Now, how do we get Imax? So the magnitude of I is actually going to be equal to our Thevenin voltage over our total resistance, which is going to be equal to 90/30J over our 30 resistance minus J40, which is our Z Thevenin, plus our load resistance of 50, and that will give us 3/4 plus 3/4 J, and so we want to find the magnitude of it. So 3/4 is going to be equal to 0.75 squared plus 0.75 squared, which is equal to 1.06 amps, which is the magnitude of our I. And so we can find now that P max is equal to 1/2 our load resistance of 50, followed by our I max, which is equivalent to the magnitude of I of 1.06 squared, and that gives us the maximum average power absorbed over the resistor is 28.09 watts. Thank you for watching the video and hope to see you next time. Goodbye.